Hello everyone, welcome back to the course Vector Calculus and Complex Analysis. Myself Dr. N.CH.Ramgopal, working as Associate Professor in Mathematics in the Department of Humanities and Sciences, MLR Institute of Technology, Hyderabad. Today, I am going to introduce an important theorem called Residue Theorem or Cauchy's Residue Theorem. Cauchy's Residue Theorem. So, using which we can evaluate the line integral of a given function f of z along a curve C. The line integral of a function of complex variable can be evaluated using the residue theorem. And what is the theorem statement that we are going to see here? If f of z is analytic on and within a closed curve C, and let us suppose z1, z2, etc. zn are the poles which are inside the curve C, and R1, R2, etc. or Rn are the residues of these poles. Then, according to Cauchy's residue theorem, the line integral of f of z dz can be obtained by multiplying the sum of the residues with 2 pi I. So, the line integral f of z dz is equal to 2 pi I into R1 plus R2 plus so on Rn. Simply, the line integral of the given function of complex variable along the curve C is 2 pi I into sum of the residues. So, this is the statement. This residue theorem helps us to evaluate the line integral. And what are the steps involved in this? First one, to find the poles. Second, identify the poles which are within C, and then find the residues of those poles, and use the Cauchy's integral theorem to evaluate the line integral. Let us solve some problems on the same. Evaluate the line integral where C is the circle mod z minus 1 equal to 3. So, coming to the solution part, given line integral is 2 e power z by z plus 1 whole cube dz. So, what is the curve C here? Mod z minus 1 equal to 3. Now, first step is to find the poles. How to find the poles? By equating the denominator to 0. What is the denominator here? Z plus 1 whole cube is 0. That implies z equal to minus 1 is a pole of order 3. So, here there is only one pole z equal to minus 1 which is of order 3. The next step is to find the residue at this pole, and we have the formula to find the residue of a function f of z at a pole z equal to a of order m. What is the formula? Residue of f at z equal to a is 1 by m minus 1 factorial if m is the order of the pole, then limit z tends to a, d power m minus 1 by dz power m minus 1, this z minus a power m into f of z. So, using this formula we can find the residue of the given function at the pole. So, residue of f at the pole z equal to minus 1 is here a equal to minus 1 and m equal to 3, because the pole is repeated 3 times. It is of order 3. So, 1 by 3 minus 1 factorial, limit z tends to minus 1, d power 3 minus 1 d square by dz square of z plus 1 whole cube into the function f of z. And what is the function here? So, 1 by 3 minus 1 factorial is 1 by 2 factorial, limit z tends to minus 1, d square by dz square of z plus 1 whole cube into 2 e power z by z plus 1 whole cube. So these two gets cancelled. So 1 by 2 into limit z tends to minus 1, the second derivative of the function 2 e power z. So that is equal to 1 by 2 factorial is 2, and here this 2 comes outside, into 2 limit z tends to minus 1, the second derivative of, so e power z, the second derivative of 2 e power z, 2 comes out and e power z derivative. So these two gets cancelled, limit z tends to minus 1, the derivative of e power z is e power z itself. So again differentiating we get the same function. So the answer is 1 by e. Now by Cauchy's residue theorem, the line integral of the function f of z dz is equal to 2 pi I into sum of the residues. So here 2 pi I into, we have only one residue, which is, so the line integral 2 e power z by z minus 1 whole cube dz is equal to 2 pi I into e. Similarly, let us solve another problem where the curve C is mod z equal to 1, and to find the poles, equate the denominator to 0. So 2z plus 1 equal to 0. By equating the denominator to 0, we get z equal to 0, minus 2, minus 1 by 2. And since the curve is a circle with center at origin and radius equal to 1, it is very clear that z equal to 0 and minus 1 by 2 lies inside the curve C mod z equal to 1. And also here both the poles 0 and minus 1 by 2 are simple poles. So simply repeat it only one time, m equal to 1. We can consider m equal to 1. What is a simple pole? A pole of order 1 is called a simple pole. Here 0 and minus 1 by 2, these are non-repeated roots, so therefore which are called simple poles. Now we need to find the residue of f at z equal to a, which is a simple pole. So simply the formula is limit z tends to a, z minus a into f of z. Now first one, residue of f at z equal to 0, R1, let us call it as R1. So R1 is residue of f at z equal to 0, which is limit z tends to 0, z minus a, so which is z into f of z, 2z minus 1 by z into z plus 2 into 2z plus 1. So here z and z cancel. So R1 equal to, now apply the limit as z tends to 0. So minus 1 here by 2 into 1. So R1 is minus 1 by 2. Similarly, we need to find the residue of the pole minus 1 by 2. Residue of f of z at the pole z equal to minus 1 by 2. So let us call it as R2. R2 is residue of f at z equal to minus 1 by 2, which is limit z tends to minus 1 by 2, and this minus 1 by 2 came from this factor 2z plus 1. So 2z plus 1 into f of z. So this is limit z tends to minus 1 by 2, 2z plus 1 into 2z minus 1 by z into z plus 2 into 2z plus 1. Now these two gets cancelled. Now apply the limit as minus 1 by 2, 2 into minus 1 by 2 minus 1 by minus 1 by 2 minus 1 by 2 plus 2. So this is minus 2 by minus 1 by 2 into 3 by 2. So minus gets cancelled, 8 by 3. So we have obtained the residues R1 and R2. Now by residue theorem, Cauchy's residue theorem, the line integral of the given function is equal to 2 pi I into sum of the residues. Here only two poles lies inside the circle, therefore we have obtained only two residues R1 and R2. So 2 pi I into R1 plus R2. 2 pi I into what is R1? Minus 1 by 2 plus 8 by 3. Now this is equal to 2 pi I into 6 minus 3 plus 16. So the line integral, given line integral 2z minus 1 by z into z minus 2 into 2z plus 1 dz is equal to 2 pi I into 13 by 6. So 13 pi I by 3. This is the integral value. So using the Cauchy's residue theorem, we can evaluate the line integral of the given function by finding the poles and residues. Similarly, let us solve one more problem. So the circle C is mod z equal to 3 by 2. So evaluate the line integral using residue theorem. And here the poles, first we need to find the poles and then identify which poles are inside this circle by equating the denominator to 0. So here of course there is a typo. So this is minus 1. Z minus 1 is equal to 0, That implies Z equal to 0, 1, 2. These are the poles. And what is the given circle? Mod Z equal to 3 by 2 means 1.5. So it's a circle with center at origin and radius equal to 1.5. But here the poles Z equal to 0 and 1 lies inside the circle mod Z equal to 1.5, and also Z equal to 0 and 1 are simple poles. So we need to find the residues of these two poles only. Here Z equal to 2 lies outside the circle, we don't consider, because in Cauchy's residue theorem we find the residues of the poles which are within the circle C only. Now to find the residue of f at z equal to 0, R1. So how to find R1? Limit as z tends to 0. So this z into 4 f of z, 4 minus 3z by z into z minus 2 into z minus 1. These two gets cancelled. Now as limit z tends to 0, this is equal to 4 by minus 2 into minus 1, so 2. Similarly, we need to find the residue at z equal to 1 also. Now residue of f at z equal to 1, which is R2. So R2 can be written as limit z tends to 1, this z minus 1 into 4 minus 3z by z into z minus 2 into z minus 1. These two gets cancelled. Now applying the limit as z tends to 1, 4 minus 3 by 1 into minus 1. So which is minus 1. Now we can apply Cauchy's Cauchy's residue theorem. So by Cauchy's residue theorem, the line integral f of z dz is 2 pi I into sum of the residues, and here we have R1 and R2. Hence the given 4 minus 3z by z into z minus 2 into z minus 1 dz is 2 pi I into 2 minus 1. R1 is 2 and R2 is minus 1. So the answer is 2 pi I. So like this, using the residue theorem given by Cauchy, we can evaluate the line integral f of z dz. and which is equal to 2 pi I into sum of the residues of the poles which are within the circle C. So first we need to find the poles, then identify the poles which are within C, then residues, and then apply the theorem. So in the next session also I am going to continue the same. We'll solve some more problems on residue theorem. So this is for today's session, and we will meet in the next session. Thank you.